Hi everyone, in this lesson we're going to investigate the shapes of binomial distributions, just as it says here in this title. So I'm not going to download this worksheet from the website. I'm going to instead use my graphing calculator for a little while. So let's move into the stats app, and I've preset here in my first list the values 0 to 10, so I'm going to do a binomial experiment with 10 trials. Now where are we? So I want the distributions, then a binomial distribution. Let's do a probability one, the individual values, not cumulative. I've set this to be looking in list number 1 to collect my data, so that's the number of trials. The total number of trials is 10, and let's go with probability 0.8. Then I'm going to save the results into list 2. So just check all of those options match, then we'll calculate. There's the probabilities of the individual outcomes, and if I pop back, they'll be stored in list 2. Now I can do a graph with F1. Now always check the graph setting. There's 3 different stats graphs that you can preset. Let's just check the settings, and I usually leave graph 1 as a scatter chart for XY data. Graph 3 I've set to be a histogram. The X values are stored in list 1, that's the numbers 0 through 10. Then the frequencies, or the heights of the blocks on the histogram, will be the probabilities in list 2. Then that's all I really change. I don't change the default colours and so forth. So now that settings are right, I can just press F3 here to display graph 3. I want to start the first histogram block at -0.5 with a width of 1, and then we just press execute, and there's my histogram. So the shape of this distribution is quite interesting. The probabilities down here for 0 successes, 1, 2 and 3 are so small we don't see them. We can start to see them here, and of course there's 10 successes. The most popular outcome, or the most likely outcome, is 8, and remember the probability of success was 0.8. So that's important. Now that's how you use the graphing calculator, but I have set it up in the spreadsheet. So up here 10, if I change that probability of success to 0.8, now I've set that to be a formula to recalculate, and each of these calculates. So there's my same distribution here. You can see that this graph is not symmetrical, it's skewed, and because the tail, the longer edge of the graph runs down to the left, we say it's got negative skew. So there's more, if you like, from the most popular one there at 8 outcomes, it's longer. The tail on the left is longer, negative skew. So what do we find about the shape of this distribution for larger values of n? Well, let's just go back to 0.5 so it's nice and symmetrical. And let's do a really low number. Let's do 6. So there's 6 trials. We could even go 4 trials. It's getting pretty blocky there. Let's go 2 trials. Wow, look at that. So 0, 1 or 2 successes, just 3 little outcomes there. So we're supposed to describe the shape of this distribution for larger values of n. So let's go the other way now. Let's go up to 5. Let's go 10, 15. Let's jump up to 25, 35, and let's jump all the way up to 50, which I've set this to be maximum 50. Now I hope you can see that the shape of this distribution, it's getting smoother because we're doing more trials. Each of the jumps from one to the next is smaller and smaller jumps, so it's getting to be a nice smooth distribution rather than being so blocky. That's the first one. What happens as the value of p gets closer to 0? So we're on 0.5 at the moment. Let's go 0.3. So it still looks fairly even, but this tail here on the right is slightly longer than the one on the left. There's a mild positive skew. Let's go 0.1. Now there's quite a strong positive skew this time. Look how much longer the tail on the right hand side of the highest outcome is compared to this one. And I could make it even more extreme if I go say 0.01, and now we've got, basically there's the most popular one is right here at the start, and then the entire distribution is to the right. So as p gets closer to 0, there becomes more strongly skewed positive skew. And I think we'll find the opposite if we go to higher values of p. So there's a fairly strong negative skew there. We could make it even more if we did that. So how does the expected value change as n and p change? Well, let's take a look at this. We have here n is 50, p is 0.8, and the most likely outcome there is 40. Let's try making that 0.6. Now the most likely outcome is 30. What if we make it 0.5? The most likely outcome now is 25. I think you can tell that the expected value, the highest probability outcome, is just n multiplied by p. What if I change that down to 20? The expected value is 0.10 there, so 0.5 times 20. So that answers that question there. Now, here's a couple of little examples of this type of work in action. So we've already seen this one here, that the expected value is n multiplied by p. The variance is n multiplied by p times q. And so the standard deviation is the square root. Those are your three ideas. That one, and that one. So the expected value, the variance, and the standard deviation of the distribution. Let's take a look at an example. In a particular binomial experiment with 90 trials, let's write down this as we go, n equals 90. The probability of success in any trial is 0.16. So straight away I'll put down q is 0.84. Remember, p plus q must equal 1. What is the expected value? So the expected value, also known as the mean, is n times p, 90 by 0.16. So we'll just go straight back to calculating here. $14.4. What is the probability that the outcome is within one standard deviation of the mean? Well, the first thing we'll need to do is work out the standard deviation. The standard deviation is the square root of n by p by q. 90 by 0.16 by 0.84. And that's 3.48. 3.48. So I now need to know that we need the mean minus one standard deviation, and that our outcome x is somewhere between the mean minus to the mean plus. That's what they mean by within one standard deviation of the mean. So I would have 14.4 minus, that's 3.5, and 14.4 plus 3.5. So what's this going to be? That's 11.4 or 10.9. And that's going to be 17.9. Now remember, with these binomial probability outcomes, they are discrete. X can only be a whole number. So do I round this down to 10 or do I round it to 11? look at the inequality sign. X must be equal to or greater than, so don't go down. This means 11. And likewise here, x, I would not round that to 18 because x must be less than that number. It can't be a fraction, so less than is 17. And that's the probability they want me to find. They want me to find the probability that x is, so the calculation above implies that the probability I seek is between 11 and 17. And that's going to be, well, as we've seen in the past, this was 90, C 11, P to the power 11, Q to the power of 90 minus 11 would be 79, plus dot 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 dot, all the way to 90, C 17, P to the power of 17, Q to the power of 90 takes 17, which would be 73. Now that would be a rather long and complicated calculation to perform step by step, but fortunately we have technology available to help us, don't we? I mean, don't get me wrong, we could key this into the calculator, but there's lots of them there to do. Whereas there's 7 of them. It's a bit time consuming. So we can use the stats menu, and by coming over here into distributions, binomial distributions, this time I will use the cumulative distribution. Data is stored in lower list, upper list. Number of trials is 10. So I don't want lists, I think I want variable data. That's it. Lower value is 11. Upper value is 17. Now I have 90 trials in this experiment. This is just remembering the last thing I did. And the probability of success was 0.16. Now I don't want to store the output in a list, so I'll say none for that one, and then it'll just display on the screen when I calculate. There's my calculation. The sum of all of those is 0.687. So I'll just write that down. 0.687. Or 68.7% probability that the outcome of this experiment is going to lie within one standard deviation of the mean. Thanks for watching. That's the end of this lesson.